All right. Let's get her in here. Okay. Okay. So, on a first thing we have is lines. Now, as soon as you're in here, we'll be able to start talking. Just let me know when you're in, and we will figure out what'll work best for you. Just say hi in chat, and then I'll know you're there. And I'm going to take a look at this picture and see if I can zoom in a bit. Angles on straight lines, around a point, vertically opposite angles, and angles in parallel lines. Okay. Are you here yet? You can just type in the stream chat, and if you're here, that would be great. Let's do it this way. Just waiting for you. Let's see. Let's see some more examples that she's got. We'll go through one by one. Let's see, what do we've got here? That's our x value. This one is our x value. And I can't read the degrees. I can't read the degrees. That's okay. We will wait for her and she'll tell me. So we're going to talk about lines. What other things can we say about lines? There's the bisecting lines, parallel lines, angles between them. This angle is congruent to this angle. This angle here would be congruent to this angle. This is angle A, this is angle B, A plus B. This is 180 because it's a straight line. A whole bunch of stuff like that. Just gotta wait patiently, I guess. I don't want to go too far into it without you here. I guess just look and see how difficult it is to make an account on Twitch. Pretty sure it was pretty easy before. Still not here. I will wait patiently. Okay, still waiting. Until she figures it out, let's look a little bit about these upper bounds and lower bounds. Okay. We said it was a maximum and a minimum. Let's think about upper and lower bounds. Now, we're doing this as like a chalkboard. And we were thinking before that, you know, we could represent it with functions. There's water. So we could say that an upper and a lower bound is like setting a maximum or a minimum. So an upper bound and lower bound is similar. Oh, wow, I wrote is twice. Interesting. Is similar to a maximum or minimum. Okay. Like a bound of functions. Let's see. That works okay. What else can we say? In words? In elements? The area is bounded by y equals a. Upper bound. And as a lower bound, y equals x is a lower bound. But there is a left bound, and that would be when x equals 0. Oh, and got an extra viewer now, so we might have her in. Anna, are you in? Are we in for our lines? If you're having trouble, just let me know. And I can see if I can help sort it out and make it easier to communicate with you. Water is in liquid state. Would be another thing of bounded. Between 0 and 100, right? This would be an upper bound. Still. Come on, you can do it. I've got your pictures, you're waiting. So what I do is I use Twitch and YouTube to do math tutoring. Now I wanted to use Discord screen sharing in private calls to be able to communicate one-on-one easily and in real time instead of having this delay. Because on YouTube and Twitch there's a slight delay. And texting is not the same as really talking. So it will be interesting to have actual conversations with people, whereas me just talking to myself doesn't really do anything. So we're still just waiting, and I believe this one was X on this one. Well, I will wait. Once you're here, we will get started. I have someone that's through Instagram wants some help. She's having troubles by the looks of it. The only problem is my YouTube link is, since I don't have 1,000 followers on YouTube, I just have the super long encoded link, which is not great for, you know, copy and pasting. Well, let's continue. Works better on a computer. I'll continue making this, I guess. I don't think having so would be correct. Okay. It sure is taking a while. Do do do. Well, while I wait, let's see if I can pull up this textbook to see if it's got any reference to this material. It's a grade 9 textbook. Area. The interesting thing is, it doesn't look like this textbook actually teaches you anything. They go through a lot of random stuff, like inquiring, but it doesn't give you a formula. It doesn't give you, like, an example even. Hmm. Area for the rectangle, for a white square. Interesting. I don't see them give anything about surface area of a circle. Nope, no formula. Literally just... Here, do this problem. Area of a circle is pi r squared. Yeah. Very condensed. Just wait, I guess. A plus 1/2 of a plus b. Yep. Times height, area of a trapezoid. Parallelogram. It's one thing. Base times height. Interesting. Ah, there's getting some volumes in here. Come on, I've been going, waiting here. Okay, well, since you're not here yet, I'm just gonna go on ahead and do some other things while I wait. And while I wait, let's think about numbers. 1729, I think, is one fascinating number, I believe. $17.29. Is the Hardy-Ramanujan number. So 1729 can be represented as the sum of two cubes two different ways. 1 cubed plus 12 cubed is also equal to 9 cubed plus 10 cubed. It's an interesting number. Apparently, it is also the smallest number. Well, positive number. Smallest number that can be represented. By the sum of two cubes. What's another fascinating number? Well, besides, well, there's the okay. I always, for some reason, in finance, it was always interesting looking at what's it called? Let's see, interest. It was always interesting looking at interest because you want to make money, right? Interest. And so if I give somebody $1, they say in tomorrow they'll give me $1.01. Let's say. So I loan them $1. Loan $1 today, get back tomorrow. Well, that's pretty decent interest for $1 in one day. Well, not really. I mean, 1%. But when you think about it, how can I maximize my interest? So let's say it's $1 today, $1 instead of it being tomorrow by the end of the year. Well, that's pretty low amount of interest. Okay, so that means that we have our current value, or our present value, and we need to multiply by some number to give us our future value. Well, our present value is $1. Our future value is $101, which means 1 times something has to give you 101, which is 1.01, right? But let's represent it as 1 plus our decimal. So this would be our 1 times 1 plus 0.01. Gives us 1.01, right? Okay. What about if instead of $1, we loaned $2? And what will how will that change our present value and our future value? Because the inside doesn't have anything to do with present value or future value. So this would stay the same. So let's do $2 times 1 plus 0.01. Well, that'll give us 2.02. Right? Okay, that's not bad at all. Now, well, that's 1 year. What about 2 years? Well, you'd have the interest on top of interest, right? So you'd have such and such amount of interest, so you'd have 2 cents extra. And you gain interest on those. So 2 years of it. So our first value for 1 year is 2 times 1 plus 0.01, which gives us 2.02. And now we've got a second year. And in the second year, we'd have that interest again, 1.01. Well, now what is the value? Well, 2.02 times 1.01 is 2.0402. So there's a little bit extra, but it doesn't really affect too much. Well, how many, if we keep going? Iterations, more and more interest. Changes our rate. So what happens if, instead of saying 1 or 2 years, let's say that interest is, we only want to work with 1 year. So let's say we want to work with 1 year. She still hasn't responded. She must be having issues. So we're going to work with 1 year, but now we're going to have 2 iterations of interest in the year. So we're going to calculate interest after 6 months and then 6 months again. It's going to be the same thing as this. So we've got 2 times 1.01 twice. Because look, this was multiplied the first time, and this was multiplied the second time. So we're going to do it twice in 1 year. It's still going to give us 2.0402. So this is interest every 6 months. Okay. Now, what if we did, instead of it twice, we calculated it every 4 months? So it would be 3 times. So 2 times 1.01, 3 times. See, there's a pattern here. 2 times 1.01 to the power of 3. Well, this gives us 2.06, but 0602. A little bit extra, not quite enough to worry about yet, but it would make a big difference if we were working with a larger number. So instead of 2, it was 200 or 2,000 or 10,000. See, that would start making a big difference. Okay. We change the interest rate, that'll make a huge difference as well. But let's see what happens if we keep going. So this is 3 times a year. And we do, let's do it every month. 1.01 to the 12 now. Well, this should make a huge difference, right? We've got interest going 12 times in the year. So 2 times 1.01 to the power of 12. Oh, you get a lot more interest. I should write it a little bit straighter, don't you think? Yeah. 2, 5, 3, 6, 5, 0, 0, 6. Okay. What about instead of every month, what if we calculated interest every day? There's 365 days, right? It's going to go up huge. So 1.01 to the 365 equals what? Well, 2 times 1.01 to the power of 365 should be very large, right? we get... Did I even type that in right? 75.56. 6.86867. Wow, what's 2 times 1.01 to the power of 100? $5. Why does it seem so ridiculously large? Did I miss a number? No? Okay, well let's go, instead of every day, calculate it every hour. Well, there's 365 days in a year, and there's 24 hours a day. 365 times 24 is 8,760. Well, I should get quite a bit, right? 2 times 1.01 to the power of 8760. Why does it seem so wrong? Oh, yes. The only thing, we're missing something here. It's 1% for the year. So we actually will change this formula slightly. 2 times 1 plus, well, the interest rate for the year is 0.01, but we're going to calculate it twice in the year, so we have to divide it by 2. So 0.01 divided by 2 squared. This one would be 2 times 1 plus 0.01 divided by 3 cubed. This one here, 12 months. 1 plus 0.01 divided by 12 to the 12. See the pattern here? This will be better. I wondered why my numbers were blowing up for some reason. I was missing an aspect. 1 plus 0.01 divided by 2 to the power of 2. This will give us 2.02005. This one will give us, oops, 2 times 3 must have typed something in wrong. Yep. There. 2.02006. Okay, this will end up getting bigger and bigger as we go. So this one, 2 times 1 plus 0.01 divided by 12. $2.02009. They're getting bigger and bigger. What about 2 times 1 plus 0.01 divided by 365 to 365? Two times 1.01 divided by 365, the power of 365. Yep, I missed a number again. Calculators. There we go. 2.0201. A little bigger, a little bigger. I guess you're not coming. Interesting. Okay. As this limit gets bigger and bigger and bigger, what do we get? Well, let's find out. Let's go to 1,000. Two times 1 plus 0.01 divided by 1,000. We get 2.0201 and a couple zeros. 2, 3, 3. So it's not getting much bigger. It's even though the numbers themselves, the iterations, is getting bigger and bigger, but it's not getting bigger and bigger. Why is that? We've got a limit here. Well, there's a limit as h goes to infinity, and there is a particular number that will give us this value. Euler's number. One plus 1 over n, the power of n. Well, instead of h, I'm going to write n. That's a little better. This is e. And what is e? E is... Well, let's pick a really big number. Let's just do 1,000. So then we plug in 1 plus 1 divided by 1,000 to the power of 1,000. We get 2.716923932. That's a pretty good approximation of E, Euler's number, which means no matter how much you iterate on the interest, you're still gonna hit a limit and not gain too much extra. So there's always the question of how much, what's the interval that you calculate interest. The best one would be as often as possible because you would reach this limit. However, the difference between 900 intervals and 1,000 intervals doesn't change much. I mean, between 1 and 10, yeah, sure, quite a bit. But you reach a point where the rate of change doesn't change that much. Actually, we could kind of draw this. Let's draw it. So our function 1 plus 1 over n to the power of n looks a lot like this. And it's getting gradually closer to this value here, which is e. And if I can draw my line a little better, getting gradually closer. It doesn't quite touch because e is an irrational number. Okay, I'll be right back. Okay. Let's continue. Whatever. Okay. We did E. We did a little bit of looking at some things. Still waiting to see if our friend here will join us. Until that time, let's do some more complicated things. Let's take a look at vector calc. I want to do some learning too. And what are we going to learn? Okay. Suppose a duck was swimming in the circle x equals cosine of t and y is equal to sine t, and that the water temperature is given by the formula T is equal to x squared e to the y minus xy cubed. Okay, okay. Find the partial of t with respect to t, otherwise known as the rate of change in the temperature that the duck might feel, by A, chain rule, and B, expressing t in terms of t and differentiating. Okay. Let's see. What do we have to do? Chain rule, right? Kind of wish I had more space. One day I'll get a bigger desk, right? You could always just say hi. Okay. Technically, we're still waiting on our one student that hasn't arrived yet. She might be having difficulties. But as soon as she types in chat that she's here, we'll go on to helping her out with her things. Okay. So we've got T. And we want to do the chain rule. How do we do the chain rule? Well, dt by dt would be what? Dt dx times dx dt plus dt dy dy dt. Well, what's the derivative of t with respect to x? So dt dx is, well, we've got e to the y, that would be like a constant. We'd have 2x e to the y, and then minus y cubed, because the derivative of x is just 1. What about dx dt? Well, we've got x is equal to cos t, so the derivative of cosine t is sine t, right? Derivative of cos is minus sine. So we've got minus sine. What about dt dy? E to the y, derivative of e to the y is just e to the y. So we've got x squared e to the y minus x, well, x is constant. Derivative of y cubed, which we'd bring down to 3, minus 3xy squared. And then dy dt, well, y is sine t, the derivative of sine is cosine. So cosine t. Now we plug it all together. dt dx. 2x e to the y minus y cubed multiplied by dx dt minus sine plus dt dy x squared e to the y minus 3xy squared times dy dt, which was cosine of t. Now, don't forget, x is cosine of t and y is sine t, which means we have to replace these values of x and y with respect to their corresponding t. So, we'll write it over here. X is cosine of t and y equals sine of t. Let's plug her in. We got 2. Well, we've got cosine of t e to the sine t minus, well, what's y cubed? So that's sine cubed t. This is all multiplied by minus sine t. Okay. Then we've got plus, x is cosine, so we got cosine squared, t, e to the sine t, and then minus 3, x is cosine t, and then y is sine squared t, and then this is all multiplied by cosine of t. Okay, now let's simplify. Multiply everything out. Okay, so 2 cosine t sine t, and this is going to be a minus, and this is e to the sine t. And then we've got plus, minus times a minus, sine to the 4th t, and then plus cosine cubed t e to the sine t minus 3 cosine t squared sine squared t. Okay. Is there some things we can do to make this simpler? Well, this looks like a double angle identity. Because the sine of 2 times an angle where can I write this? This is a double angle identity. Sine of 2x is equal to 2 sine x cosine x. Okay, which means this right here would be 1/2 of sine squared of 2x. This right here would be sine of 2x over 2. You know what? Let's actually look and see if it's even relevant to simplify it. They don't care. That's our answer. I would simplify, but they don't care. Okay, we did it with chain rule. Now we have to do it the other way by substituting in and then differentiate. I'm going to write it again. So t equals, what is it? X squared e to the y minus xy cubed. Yes. And x equals cosine of t, and y equals sine of t. And now we need to just plug it in. Hey, boss mom! How are you doing? I don't mind that you're lurking. I'm actually waiting for someone. I had another person on Instagram ask if they could get help. They're in the UK. But apparently she's having trouble connecting, or she changed her mind once she organized. I'm not sure. Okay, so we got to sub in these values and then differentiate with respect to t. So our t, our temperature, will equal, well, this is cos squared of t e to the sine minus cosine of t y cubed, which would be sine cubed of t. Oh, you're gonna do a vlog? Yeah, I'll go over simple math. I'll tell you what. I'll finish this one because this is an interesting vector calc, and we're showing two different ways to do a differentiation. I was actually spending time before thinking of things that I could do with you to talk about simpler math. But I'm just going to differentiate this. And the thing about this is you have to kind of know the basics of differentiation before you can do the vector calc stuff. So this is like a second year course. Okay, differentiating, product rule. So we've got two functions. The derivative of two functions is f g prime plus g f prime. So we're gonna differentiate both of them. Okay, now our f would be our cosine and our g would be e to the sine t. I don't know, this is a little difficult to follow along if you've never done anything like this before. But well, I'll try. I'll try and do it a little slower. So our f function will be this cos squared, and our g function will be this e to the sine t. So using this formula, we want to take the derivative of these multiplications. F will come down first, so we just got cos squared of t. Then we need to take the derivative of g, which is the e to the sine t. Now, e to the x, the derivative of e to the x is actually just e to the x, surprisingly. So then this is just e to the sine t. However, you have to multiply by the derivative of the top. It's the chain rule. Don't worry, I'll go back to the very beginning of things that'll get you up to calculus. Maybe. We'll see. We'll go through some functions and numbers and stuff. Okay. So we need the derivative of sine. And the derivative of sine is cosine. So there's our first part. Now we need the second part. G, which will be the same, e to the sine t. Now we need the derivative of cosine t. And this is cosine squared t. So this would actually be a combination of power rule and chain rule. So if I just do it, we'd get a 2 cosine of t. And then the derivative of cosine is minus sine. So we'd multiply by minus sine t. And that would complete our first part. Now we do it again using the second part. So plus. F would be our negative cosine of t. And G would be our sine t. And we go G first. So sine cubed t times the derivative. Oh, I'm doing backwards. F first, so we've got minus cosine of t, derivative of sine cubed t, which we'd bring down the 3, sine squared. Derivative of sine is cos, times cosine t. Again, now we've got g f prime, so plus sine cubed t, f prime, derivative of cos is minus sine. So we'd have a minus times a minus would cancel out, so I'll just write sine t. And now if we simplify, this is our sine to the 4th. I should probably write that a little nicer. Which is checked, it's right up here. This one right in here will give us minus cos squared t sine squared t. And we've got our 3, so this is the same. Check. This right here is this one up here. Look, minus sine t cos t e to the sine t. Check. And then cos cubed sine t. Check. This is 2 different ways. No worries. You go make your call. I'm just about ready to go work on some lower stuff. Okay. Just for boss mom. Okay. Boss mom Do you want to have like a conversation? Because what I can do is I can talk to you directly and screen share with you through Discord if you'd like. And that way you don't have to worry about delay or anything. If you're not busy and you actually want to go through things, if you're just doing this on the side, then we'll just go through the stream. It's up to you. Because what I was thinking about was gauging where you're at. Now, logic things. We could discuss functions in general. Moving things. Okay. Now, you said before, like, early algebra stuff, right? And using simple things. I'm going to start by saying that X and Y are called variables, right? They represent a number. We just don't know what that number is. But they could also be used as a relation to something else. So if we say y equals x, we've got two variables. They can be anything. So 20 minutes? No problem. Okay. Boss Mom, let's have a little conversation and I'll figure out some stuff. Okay. Oops. There you go. Yeah, no worries. 20 minutes should be more than enough time to get started on something. So I sent you a Discord link. You should be able to click on it, and this is my Discord channel where we sometimes converse. And I sent it to you in Twitch chat, Twitch private chat. What else can I say? Yeah, you found it. Okay, I am just going to give you a quick call, and then I will turn on my screen share.
Can you hear me?
Yes, I can.
Okay, awesome.
That's okay. Okay.
Right.
So tell me about what you really want to learn a little bit about. Like like logic?
You know what? I'll just be frank. So I was in
Mm-hmm.
okay until freshman year. Then I decided I wanted to be in school,
Okay.
and I went to like these co-op groups, and I had the option. I could do basically whatever I wanted to do, and I never liked math. So I was like, I'm doing math again, and that's what I did. I stopped there.
Okay.
So I kind of what I want to do is like go back to where I was. I guess that was fun. I want. I'd like to understand um, the business world, like finance side of things. But I feel like I don't even know where to begin.
Okay.
Like, math wise, no idea.
I definitely know what we can talk about when it comes to understanding the business world in math, especially like
Okay.
early stuff. So we're talking like economics and
Okay.
understanding graphs and understanding data. Does that make sense?
Yeah. Yeah.
Okay. Then simple stuff to begin with. So on my screen, I've written x and y are called variables, right? They can be anything as long as you understand that they can be anything. So x and y are just variables. P and q is the same thing, it's just a different letter.
Okay.
Okay. I could also, if I wanted to, I could draw a box and say that's a variable. I could say a bunny rabbit is a variable. If I can draw a bunny rabbit.
That makes sense.
Okay. Terrible bunny rabbit. But you know what I mean?
Yeah, I know it.
Okay. So variables is just how we communicate that it's something we don't know. Okay? It's also a way we can communicate there's a relation. Now, a common convention is to just say x and y and z and t and p and q and all these letters. Okay? That's just common.
Okay.
Now, sometimes in the math world, you'll have a function with lots of variables. And usually the way they represent it is by saying f of x or f of t, or if it's multiple, f of x comma y, etc. All that really means is that it's equal to some kind of combination of x's with varying degrees of power, or t's, or a combination of them. So
Okay. Stop you before I get ready to.
no, that's okay. I want you to stop me.
I apologize. I want to.
Yeah, it's okay.
Whatever I want, whatever I want, whatever I want, whatever I want.
Pretty much. It's
Okay,
it's just like a definition of what it means. So we're on a common language.
Can we like? Can you just explain? Make an example.
Well, sure. So let's just say that y is equal to x. This is the standard line function.
Okay.
Okay. So what that means is if you take and you draw a graph with a y-axis and an x-axis, the relation between x and y is the fact that whenever there is an x value, y is the same value.
Okay.
So if we draw like a table of values, if we say y is equal to x, and we want to look at different values to work with, we would start with like 0 or 1 or 2, and we'd say, what is the corresponding y value? So we'd look at the formula and we'd just plug it in. 0 is 0, 1 is 1, 2 is 2, all the way along.
Okay.
Okay. What that means then is we have values that correspond to a graph. And if I draw it correctly, which I'm trying.
Uh-oh.
That's okay. There.
Can you hear me?
Yep, I'm still here.
Sorry, I lost you.
It's okay.
Alright, so you were saying the last word correctly?
Yeah, if I can draw the graph correctly, which I have now. So on the screen, you see this line that's got like a 45-degree angle.
Yes.
So what this is representing is for every value of x that you plug in, it gives you the corresponding y value. So like here's 1 and 2 and so on and so forth. And y has values 1 and 2 and so forth. Okay? So it's like working in a two-dimensional world. So another way to think about it is a number line. If we say x is equal to 1, then and we just have our number line 0, 1, 2, 3. It's just corresponding to that one variable, that one number.
Makes so much more sense because it's a lag screen.
Yeah.
So, like once I can actually see you plugging. Okay.
Yeah.
I'm here. I can along.
Cool. So basically right now I just want to make sure we're on the same language.
Okay.
So a lot of it right now is just kind of like definitions and saying this is what it's called.
Yeah.
Okay. Once we're past that, then we can start talking about how to work with them. Okay.
Sounds easy.
Honestly, that's math is a language, right? That's okay. So what I've started here is to say that you can have a function of variables. So the simple one was just saying y is equal to x. So our function y is equal to x. Okay? If we change it to be something else, like y equals x plus 1, let's say, then it's just our function is now just x plus 1. So if we plug in our table of values, x and y. So if x is 0, what is y?
I don't know. I'm confused.
Okay.
He lost me.
That's okay. That's okay. This is helping me gauge your understanding. So, I want you to understand. So, remember how I said it could be anything, like a bunny rabbit or a square, whatever. So, y is like our answer, okay? It is equal to whatever we do on the right-hand side, okay? So if I say y is equal to 1, that means the simplest form, 1 is equal to 1. Right?
Okay. Yeah.
Okay. Now, let's say we don't know what the number is. So we'll say it's X. We're still got something to plug in. We're still going to play with it. But we need something to have a placeholder. Okay? Does that make sense?
Yeah.
So now I'm going to add a number to it. I'm just going to add 1. So that means for whatever number we plug in for X, we have to do all the operations on the right-hand side to get our Y value.
Okay, that makes sense.
Okay.
So is it basically you have? This is always what happens in school.
That's okay.
So how are we right now? We're basically proving how out there.
No. So that's they're separate. So
Okay.
what I'm doing is going through separate examples. Y is equal to 1 was just like base. It's equal to some constant number. Nothing changes. That's it. Okay. Now we're at slightly different, where we have a variable in here, and we can pick whatever number we want to plug in. Okay. What that means is, remember before before I said y equals to x, and we plugged in 0, 1, and 2, and it just turns out it was the same, right? Y is equal to x. Well, that's just a very base, simple line where every value you plug in for x, it's just going to equal the y value.
Oh.
Okay. This one now, and when y equals x plus 1, you realize it's not going to be the same anymore because there's this plus 1.
Right.
Okay. So if we've got to our table of values now, let's say we plug in x equals to 0. What does our y value equal then?
Is it 0?
What you plug in. So if x is 0, we're just going to rewrite the equation y equals 0 plus 1.
Oh, we're still on the plus 1.
Okay. Yeah. Just going to stay at the same for now. That's okay. So what does this equal then?
What does y equals?
0 plus 1. So now y equals 1. That makes sense? Okay. All I'm doing...
Hang on. Does it... Okay. Is the reason why y equals 1 because we're basically the 0 of the same x, we're just...
Yeah, so...
Okay.
So basically... We are now substituting a real number in for the variable.
Okay.
Good. Because part of looking and finding out things is guessing and checking, or just seeing what happens when you plug in a number.
Yeah.
Okay. So like when you go into a calculator and you just want to type something in, what do? Just type something in.
Yeah.
So that's exactly what we're doing.
It's like so simple now that you think of it, but just I always feel like math is...
Everybody thinks that way. But in truth, math is not trying to trick you. It's just an awkward language that you have to get your head around.
Yeah.
Okay. The problem is lots of times people don't realize that a variable is just a placeholder. We can plug in anything we want for that.
Yeah.
So just like we were doing now, what happens if I say x is equal to 1? what happens to our y?
Doesn't change, right?
Well, now instead of x being 0, x is 1.
1. So y equals 1.
Well, no, plus 1, right?
Plus 1.
So it would be y is equal to 2.
Oh. I'm not. Sorry, it took a second for it to pull up on my screen.
That's okay.
Did you put it? Did you?
Yeah, I'm on the bottom. I feel like in Discord there is a bit of a cover on your phone, like the call buttons cover it.
I'm watching on my iPhone.
Oh, okay. So the function that we're working with. No.
Okay. I told you I was.
No, that's okay. This is good.
Okay.
It's a learning process for me too.
Yeah. Really foreign to me. Alright, so your variables are like x or y equals x. The x is placeholder for our number.
Yeah.
Now, where do we get our number?
So the function that we're working with. So y is going to be our answer, let's say. Y is our answer.
Okay.
Now the only thing is our answer depends on what we plug in for x.
Okay, but here's what I don't understand.
Okay.
How do we know what y is?
Because it's so an equal sign, right? Y is equal to whatever we have as our function. So right now, our function is just x plus 1.
Okay, our function is x plus 1.
So whenever we plug in a value for x, we just add 1 to it, and that'll be our y value.
Okay. Yeah, I just don't understand why I don't.
Okay, okay.
For me, I'm just like, well, I feel like what would be this for specific real world? What can I make a like a skill example? Figure out.
Okay, supply and demand. Let's say you, I don't know, let's say you make necklaces or something.
Okay.
Okay. And you supply necklaces, but you only want to supply them if you can get a certain price for them, right?
Right.
Because you're not going to work for free. You want to make some money.
Right. I gotta make money for labor and tools.
Yeah. So
would it be? Would y be? I guess. I'd be my how much money I'm going.
well, let's go through it. Let's figure it out together.
Yeah.
So I'm gonna make this bottom axis our quantity. So like the number of necklaces we make. Okay? And on the upper axis, I'm going to call it our price. So the higher the price, the more we're willing to make, right? The lower the price, the less we're willing to make. So as a line, we would have this kind of graph. We'd say the higher the price, which would be corresponding to the left side, the more we would be willing to make. So the further it goes along the graph. So if we wanted to, we could say that our price is equal to some function of x. We'll say it's 1 to 1. So to go along with our graph, let's say we make $1 per necklace we make.
Okay.
So if we make one necklace, we get $1. If we make 2 necklaces, we get $2. See? That's exactly what we're working with.
Okay.
But now let's say it wasn't just simple 1 to 1. Let's say we didn't want to start that low. What if we wanted to start a little higher? So instead of starting at 0, we'll start at $1 and work up from there. You see how that changed?
Don't see it, but
Yeah, that new. Okay.
I'm trying to follow the graph. It hasn't.
No, that's good. That's okay. So what has happened in our real world, we are using this line graph to determine how much we want to make a quantity of. So we'd look and say, well, I want to make at least $10. How many of these do I have to make? You just follow, you find your value at $10, and you go along until you find what's your quantity. Okay. Or you can say, I've made 20 of them. What's going to be my price that I make? You know? So there's this relation between the two numbers. Now, this is just this simple straight line relation. There's many others, but we won't get to it until way later.
Yeah, I understand.
That's okay. Basically, all we're doing is saying just finding a relation between our up and down axis versus our left and right axis.
Okay.
Is that okay? Thinking
better.
good. Okay. Now I want to go back to our original little problem. So our y equals x plus 1. Okay, that's what we're going to work with. Our function is y equals x plus 1.
Okay.
So let's say I have 10 x's. How much y do I have?
Y equals plus 1.
Right, which is?
11.
Good. So when x equals 10, y is 11.
Woohoo.
Okay. Now what if I change the function to be something else? Just a little bit different. So now instead of we have y equals x plus 1, we now have y is equal to 2 times x. Okay.
Now I have to figure out what x is.
Yes.
Okay.
So now we're still going to we're going to plug in an x value first, and we're going to see what happens. What is x equal to 0? So when x is 0, what is y?
1.
In this in this
Times 2.
so 2 times 0, right? You're plugging in 0 for x.
Okay, yeah.
Okay, so what is y equal?
0.
2 times 0.
2 times 0.
Yeah, so what is 2 times 0?
2.
Anything times 0 is 0.
Is it?
Yes.
Okay. That's sad. That's that.
That's okay.
Sounds like so simple.
Um,
Oh, duh.
yeah,
Because I'm thinking not. Like, okay. Yes.
okay, good. Now, what happens if I plug in 1 for x?
Then it would still be. Wait.
You just, yeah, no, it's okay. What I'm going to show you here.
Wouldn't it? Hang on. So, if you're timesing by parentheses guy
Mm-hmm.
is the number that you're timesing by, would it be 1 or 2?
Okay, so we are going to plug in the number 1 for everywhere we see an x. Okay? Everywhere we see an x.
Okay.
Okay, so in our function, where do we see an x? No, yeah, you have a little delay.
That's a long delay.
Yeah, it might be like 20 seconds or something. Which is, yeah.
But if you're timesing by 1, though, wouldn't it still be 2?
Yes. So our y is now 2.
Okay.
Okay.
Well,
What happens now if we, so I'm going to rephrase it a little bit for you. When we plug in x equals to 2, what is y?
two.
So y is equal to 2 times x, right? If we replace x with the number 2, what is y?
Hang on. Hope no one's watching me now. Alright, so x, which is 2.
No,
So
we
then timesing, so the 2, that's y.
Yep.
Would it be 2 times 2?
Correct. Yes.
Okay, so would my y be 4?
Yes.
Okay.
So all we're doing is substituting in numbers for x and finding out what happens to the other side. Okay? We can go into a lot of detail that will just be working with these simple 2 things from the original. So all we've done is figured out what happens if we add a number to it and if we multiply a number. Okay, now I'm going to add them both together. Just to make sure you understand, we're going to go and have a new function. And our new function is just going to be y is equal to 2x minus 1. Okay? What happens if we plug in 0 for x?
0. Okay, hang on. I gotta wait for you to write this down.
Okay. So y is equal to 2x minus 1.
Okay. Now,
We are going to plug in 0 for x. What is y?
but where's, what do you mean A? I don't see A.
X. I'm not...
Oh, I'm hearing A. X. So sorry, what are we plugging in for X?
We're going to start with 0. Plug in 0.
But I don't know what. When I put a 0 for the X, that was.
It's the multiplication, remember? So it's...
Oh, wait, what? How do I know?
So in a standard convention type deal, we actually don't write a multiplication sign when there's a variable. Because remember, the multiplication sign is an x.
Yeah.
Right? Sometimes you might write a dot to mean multiplication. So like 2 dot x. But as a convention, we don't bother with that. We just write a number times a variable is just 2 times the variable.
Okay, well, it makes sense to me. I guess for me, still like.
That's okay. You just haven't done it in a long time.
Well, yeah, I know. Your multiplication sign. I just all the adding, subtracting, and multiplying. I'm still looking for you telling me what it is. And it's
Yeah.
something.
Yeah.
Okay. So what is my? Did you just add the X?
0. So we're going to start with the simple one, 0.
So then.
Yeah, exactly. Okay. What happens when you plug in 1 for x?
Then that was 1.
Good. What happens if you plug in -1 for x?
Then you would have 0.
Try again.
No, hang on. How do you do that?
Okay. So the thing about plugging in numbers and variables and all that stuff is you literally plug in the entirety of the value or the variable or the parentheses or the function, whatever it is, the entirety of it for just the letter itself. So for an example, if we're going to have 2 times x and we're going to say -1 is x, we have to plug in the entirety of what's in the parentheses. So we'd have 2 times -1. Okay. Now I'm just gonna go a little bit further and say x is, I don't know. X is a B plus a happy face. Okay. It makes no sense whatsoever. But if I plug that in, it's just the same. 2 times B plus a happy face. All I'm doing is plugging in whatever is there for x into the function itself. Okay. So now, what happens when you plug in -1 in for x? Well, okay. On my screen, I'm going to write in here y equals 2. Now we're plugging in, so x is now going to be completely replaced by -1. Okay. Holly isn't funny. Yeah, math streams are pretty hilarious. They are.
I mean, doesn't get me. I haven't done math ever since there.
That's okay. Okay. What is the value for y?
Oh my gosh. I'm sure it's so simple, but it looks so difficult.
Oh,
Okay, so 2 times negative thing. Would that be 1?
no, -2.
It would be -2.
Yes.
Okay. I'm thinking subtraction. That would make sense. Thank you. So it'd be -2, and then are you subtracting from there? You're subtracting 1.
Correct.
So would that be -3?
Yes.
Okay.
Okay. So the funny thing is this is like helping you remember just your order of operations.
Yeah. I'm like seriously. I did subtraction when I'm supposed to do it.
It's okay.
In my brain.
It's okay. So
Okay.
I'm gonna do a little test. That's just as like a little side note for you. Okay, we've got a -1 times a -1 equals what?
1.
A negative times a negative is actually a positive. Yes.
No? Okay. Now I get it.
Okay. Holly, she finished her math minor and trigonometry wanted to make her quit. That's funny.
High school made me want to quit math.
No. Math itself made you want to quit math.
That's true. That's so.
But honestly, the truth is, I'm gonna tell you that math in high school is so there's a relation between math and art. Okay, if you take art in high school, the art teacher will show you famous paintings, famous sculptures, all those things, right? And you'll be like, yeah, that's inspiring. You wanna be like them, right? Well, math in high school is the equivalent to being taught how to paint a fence. So all you ever learn in high school is how to paint a fence. It's not that inspiring, is it? It's not that interesting, is it?
Also, like, don't, it was always, or after school, like, I couldn't ask questions like class.
Yeah. So,
I like that my school.
but like, do you understand the relation that all the math you learn early is very rudimentary. It doesn't really do much in terms of inspiring. If I tell you to look up the word fractal and just go to Google Images, you would be amazed by what that even means. Fractal. Pythagoras 2, 34 times 3? I don't know what you mean by that. One semester left and you'll be a teacher. English to everyone. Wow.
Oh, well, it's really pretty.
Fractal is mathematical.
Got pretty pictures. It's what, the curve or.
Mm-hmm. It's basically a shape that never ends. It's
like one of those little, what is that scope thing called?
like a gyroscope, I think.
Is that what it?
I don't know the scope name, no. But I can show you something that is also interesting. that's everywhere in nature. Have you ever heard of the Fibonacci sequence? Okay. The Fibonacci sequence is just a sequence of numbers where to get the next number, all you do is add the previous two numbers together. Okay. So starting with 1 and 1, 1 plus 1 is 2. Okay. The next number after that would be 1 plus 2, which is 3. Then 2 plus 3 is 5. 3 plus 5 is 8. 13, 21. You get, yeah, you get the picture. It just goes on forever. Okay. Funny thing about this sequence of numbers, it appears everywhere in nature. And these numbers also help make up what's called the golden ratio. So if you look up the golden ratio, even in Google Images, you'll see that that also appears everywhere in nature. And it's actually the ratio that is most appealing to our eyes. So like you could apply the golden ratio to the Mona Lisa or famous paintings, famous sculptures, and it creates a ratio between different parts of them. Yep, they did one of Donald Trump's hair. Okay. Are you out of time? You're done for now? We just, whenever you want, we continue.
When do you stream next?
Right now it's sporadic because I might have to go cut down trees tomorrow.
Would you be on Discord? No. Do you know?
Yeah, sure.
Okay. Because I'm taking it, but I'm liking sitting with this.
Oh, I'll try and help you get to like easy logic and understanding.
Yes. Thank you so much.
You're very welcome. Okay. SMRT.
All right, you have a good one. Thank you so much.
Yeah, you're very welcome.
Wait, I could have watched it on Discord this whole time?
Yeah, that's why I had the screen share. Because the screen share doesn't have a delay as much.
There's like no delay. I'm still really not listening actually. Gosh. Okay. Now I'll know next.
Cool.
All right. Thank you.
You're welcome. I'll talk to you later. Okay. Back to streaming. Okay, I was doing vector calc first. Because I haven't got anything else coming up recently. Okay. Back to vector calc. Well, what I've been doing Hey, host. Thank you, bud. Dadbod 2.0. Welcome. I love that. Okay. What should we work on? Because we were going to tutor someone else, but she has yet to message me back on Instagram. Okay. Maybe we go back to, oh, I don't know. Continuing with vector calc, I guess. Or we could maybe work on statistics, the actuary exam P. I was looking into a bunch of those problems too. Well, let's just keep going with this. Maybe we'll find some answers. You know, to life and everything in between. Path? We've got a path. Okay. Let F be from R2 to R2. We've got X and Y is mapped to e to the X plus Y and e to the X minus Y. Let C of t be a path with C of 0 C of 0 is 0, 0 with C prime of 0 equal to 1, 1. What is the tangent vector to the image of C of t under F at t equals 0? That sounds like a mouthful. What is the tangent vector to the image of C of t under F at t equals 0? Okay. This itself, I'm not even entirely sure. What should we do? Well, let's look it up a bit. So we've got images, and we want to find the tangent vector to the image. Something tells me we need to use a chain rule. I'd assume so. What question are we even doing? Okay. Something tells me chain rule. Just because, you know, it's the just so happens to be the section we're working under. So let's play with it. Now technically the answer is supposed to be 2, 0. So let's see if we can find the answer. So we want a path, tangent vector to the image. Well, C of 0 equals 0, 0. C prime of 0 is 1, 1. We've got X and Y going to e to the X plus Y and e to the X minus Y. Well, e to the X plus Y at 0, 0 is 1, 1. And let's see, what happens if we differentiate? I just want to play with it. If we differentiate the x1 with respect to x, we've got e to the x plus y. And this is xy. Well, let's just say f differentiated. And this one would be what? Negative e to the x minus y. C of 0, 0. C of t be a path, blah, blah, blah. And f prime of 0, 0. So f of 0, 0 would be 1, 1, right? E to the 0 and e to the 0, 1, 1. Let's try f prime of 0, 0. Would be, well, 1, negative 1. Tangent to the vector of the image under f at t equals 0. Tangent to the vector would mean the derivative What else? What else could we do? Honestly, I've got to relearn this stuff too, so you might as well tell me if you can. Yes, right formulas. We've got matrix multiplication. Derivative matrix of f maps the tangent or velocity vector of a path C to the tangent or velocity vector of the corresponding image path P. So let's try a little something else here. Well, there's more of you that have shown up. What should we do, guys? I'm just messing around. I'm going to do this matrix here. And I'm going to take the derivative with respect to x of the first one. What is it? D by dx. D... Do I want to say dx? D by dy. No, I want first variable, second variable. Pretty sure. If I can go off by memory. D by dx, so we've got e to the x plus y and e to the x plus y. This one would give us e to the x plus y and minus e to the x plus y. Or minus y. Silly brains. X minus y. And no, that seems incorrect. I gotta look at the matrix again. Why don't I remember? Variable 1, variable 2. There we go. This would be f1. F1. Brush, F1, F1, df2, dx, and df2, dy. There we go. Brush. Function 1 with respect to x, to y, we're good. This would be e to the x minus y, and this would be minus e to the x minus y. Good. And we're going to plug in 0, 0. Well, I'm going to evaluate it 0, 0. This would be 1. This would be 1. This would be, well, take a look. That would be 1 as well. And this would be minus 1. And we're multiplying onto a vector. Now let's see. The column vector I wonder if, let's see, e to the x plus y and e to the x minus y, and 0, 0 would be in that matrix. This matrix here, c prime of 1, 1. So let's plug in 1 and 1. I'm just doing basic methods to see if I can figure it out. So this would be e squared. This would be e squared. And this would be 1, and this would be minus 1. Now we want to get a vector with 2, 0. What should we do? This one here. Oh, I see it. Ah ha ha. I see it now. Plug in 0, 0. We gotta multiply by the c prime of 0, which is 1, 1, which will give us what vector? It'll give us row by column, right? So 1 times 1 is 1, plus 1 times 1, which is 2. And then we've got 1 times 1 minus 1 times 1 is 0. And we've got this vector, 2, 0. Interesting. Gradients and directional derivatives. Vector space. Okay. I'm not seeing too much in terms of extra requests today. Let's see how Trey's stream is doing. Apparently he was doing his birthday stream, so I think we should go say hi. Okay. Cool. Looks like he's doing pretty good. Okay. Let's see. Gradients? I wanted to go through something completely, though. Okay. Let's go through this completely. Grade 9. We got grade 9. What are the concepts that they have to learn in grade 9? If we look through the textbook, let's see. Numbers. Estimating and calculating square roots, applying square roots, problem solving. Let's see. Chapter 2, patterns and equations. Using equations to solve problems, polynomials, special products and factoring, measurement, shape and space, data analysis, transformations. Okay, let's see. Let's do this. Chapter 1. What do they want to start with? Mental math? Okay, let's do mental math. What is 3 times 25? Well, that's 75. Is there another way we could write it? What about 3 times 20 plus 5? What's the same answer if we go back, right? 3 times 25 is 75. But what if we distribute the 3 onto the 20 and the 5? Just like so. Now, in this question, it doesn't make it any easier. Because, I mean, this is 3 times 20, which is 60. 3 times 2, right? And add a 0. And 3 times 5, 15, 75. Okay. This is numbers. What if we did something like 7 times 45, mental math? Well, to me, that seems a little difficult to multiply in your head, right? But what if I said, what's 7 times 40 plus 7 times 5? Well, 7 times 4 is easy, right? That's 28, so 280. Add a 0. 7 times 5, well, you learned that early, well, that's 35. Well, now you only have these two numbers to add together. Well, that would be what? 310 and 15, right? Boom. What about... What if we did a number like 15 times 42? That seems pretty difficult, right? Well, it's 15 times 40 plus 15 times 2, right? Which, well then, what do we do with that? 15 times 4, well, that's an easier number for us to work with, right? 15, 30, 45, well, 60. So 60, add a 0, 600. 15 times 2 is 30. There we go. Add them together, 630. Now, there are other things we can think about as well. the question I would have to you then is, if it's 15 times 42, we got that. What if we did 15 times 42 again, but instead of breaking it up into 15, we said 10 plus 5 times 40 plus 2. Well, it's not going to be 10 times 40 plus 5 times 2. That's not right at all. Look, that's only 410. We're missing quite a bit. So when we do it this way, we actually have to, you know, FOIL it out a bit. So 10 plus 5, 40 plus 2. I know it seems complicated. This is more complicated to do in your head, but that's why I would stick with like the 15 and just split it into 40 and 2. Numbers that'll make it easy. We'd have 10 times 40 and 10 times 2, and we'd have 5 times 40 and 5 times 2. So 10 times 40 plus 10 times 2 plus 5 times 40 plus 5 times 2. Well, 10 times 40 is what, 400? 10 times 2 is 20. 5 times 4 is 20, add a 0, 200. 5 times 2 is 10. Well, there's 30, 630. They're equal. It's interesting what you can do when you start manipulating numbers. Okay, let's look at this textbook. Estimating and calculating square roots. Now, I'm not sure about this. Why would you estimate so early without, you know, thinking about it first? Estimating early. So they want to estimate okay, they want to find the square root of 81 by estimation. Now, of course, we already know that it's 9. The funny thing is I feel like it would be easier if we said that this is the square root of 81 is equal to some number times itself. Or, let's see, this some, how would I put this? 81 is equal to some number times itself. Okay. Which would give you, I feel like it would give you a different understanding of how to estimate this number, because you'd be looking at saying, oh, it's some number times itself. So like 1 times 1, or 1.5 times 1.5, or 7.5 times 7.5. You know, easier to estimate and understanding. The only thing is, they want to start with, okay, to estimate. Let's find squares that we know. We go, well, 10 squared is 100. That's too high. Let's do another easy one. 5 squared is 25. That's too low. 6 squared, 36. Too low. We could do a method where we'd go in between. So we'd try difference between 10 and 6 would be 8 in between them. So we'd have 8 squared. Well, that's 64. That's too low. So then let's try in between that. 8 and 9. Or 8 and 10 would be 9. So 9 squared is 81. Which is right. So square root of 81 is 9. Interesting. What other things they want to do? Let's figure out what they're talking about when they come to this approximate equal to. So they've got, what is the square root of 567? For numbers less than 1, estimate the square root of the non-zero group closest to the decimal point. Not considering. Consider the two groups 15 and 35. Square root of 15 is approximately 4. Okay, so they say square root of 5. Well, that's close to 2. It's approximately 2. And then they have 67 goes to 0. What is the logic behind this? So then they say the square root of 567 is approximately equal to 20. Which is odd, because I don't think it's approximately 20 at all. Groups of 2 digits starting at the decimal point. Then for numbers greater than 1, estimate the square root of the group furthest from the decimal point and add 1 0 for each other group. This is a group of 2. So you add 1 0. And then you square root of this. It's not a very good approximation. I see what they're doing. I mean, if your margin of error is 20%, then I guess that's okay. Okay, so I've got a message. Which one does she need to know if it's right or not? Shown is a right triangle. Work out the size of angle Y. Okay. Okay. I just got a question. So we've got this triangle here. This is a 90. This is 38 degrees. And then this would be our angle Y. 90 and 38 is what, 128? Which, in all the interior angles of a triangle add to 180 degrees. Okay. So 90 plus 38 is 128. 180 minus 128 is 52. So y is equal to 52. Let's see, what else does she have? Work out the angle of x. Okay, here's our triangle. And it's not a right triangle, but this is x. This is 48 degrees. And this is 86 degrees. So again, all interior angles add up to 180. We've got 180 minus 48 degrees minus 86 degrees equals 180 minus 48 minus 86 is 46 degrees. Then, shown below is an isosceles triangle. And so this is equal to this. And here is our angle y. And this is 77 degrees. Well, isosceles triangle means equal length. Equal length equals... She's got her numbers a bit backwards. She's got it right though. Equal angles. So this is 180 minus 77 equals 180 minus 144. But that's 36. And the last one . 82 isosceles, and W. Okay. This one, there's two W's that, so there, since we need to explain this to her. How are we going to explain it to her? 2W plus 82 equals 180. Or 180 minus 82 is equal to 2W. So that's what, 98 equals to 2W, and W equals 98 over 2, which equals what, 49? Okay. Let's make a post for her. This guy didn't really respond, so I'm not entirely sure what he wants. So I'm gonna just get rid of this. Okay. Interior angles of a triangle add up to 180. Oh, well, if they're on a flat surface, right? For all triangles. Let's see. That means we'll go with these 4 examples and we will just do them. Good. This is 38 degrees. This is a right triangle. Right? That's a 90-degree angle. What is the value of y? So 180 equals y plus 90 plus 38. So y is equal to 180 minus 90 minus 38. So y is equal to 52. Okay, next one. Okay, so we gotta start with the triangles first. We'll do the isosceles. Okay. So we've got this triangle, and it's not a right triangle. This is 48 degrees. This is 86 degrees. And this is x. So that means 180 equals x plus 48 plus 86. I gotta make it look better. Okay. Which means x is equal to 180 minus 48 degrees minus 86 degrees, which x equals 46. Next triangle. An isosceles triangle. So here we will do this. This will be y, and this will be 77. OSCELES. Ha! Two sides same length. Two angles. So then y plus 2 times 77 equals 180. Which then means y is equal to 180 minus 2 times 77. Which equals, what did I say, 36? Yeah. Okay, last triangle. It's another one like this. Pretty close to isosceles. This is 82 degrees. Well, 82 degrees plus 2w equals 180. So 180, or w, should probably say. So 2w equals 180 minus 82. 2w equals 98. W equals 49. Okay. Let's double check and make sure we didn't screw up any numbers. Good. Good. Good, and good. Easy. Okay. How does it look? Good. Okay, let's see what else she's got here. See if we can figure it out. Finding the whole given percentage. If what? Okay. Okay. We've got percentages here. If 53% of a number is 53, what is the number? Okay. 1. Let's change our colors here. Okay. If 53% of a number is 53, what is the number? Okay, so 53% times some number x is equal to 53. What is x? Well, remember, what is a percentage? 100% is equal to 1.00. 53% is equal to 0.53. Right? Percentage is just move the decimal place 2 places. So this is 0.53 times x, which equals 53. So let's divide. So x equals 53 divided by 0.53, which gives us 100. Okay. Let's do another one for her. If 5% of a number is 57, what is the number? So how would we say this to make it easy on someone? Let x be the number. Okay, so then 5% times x is 57. 5% is equal to 0.05. So then we have divide. So 0.05 times x is equal to 57. Divide by 0.05. They cross out. We get 57 divided by 0.05. Okay, there's a start. That's the first two. Okay, bronze. That was that first part. Let's see what's the next part. That was, now we're going to do silver. A shirt has been reduced by 40% to €7. What was the original price? Okay. A shirt has been reduced by 40% to $7. I'm gonna just say dollars because that's easier for me to write. What was the original price? Okay. The original price, well, let's think about this for a second here. Let x be the original price. So we've got let's do how would we say this for someone that doesn't quite understand? The original price, x, times something gives us $7. And we're reducing the original price by 40%, which means It was at 100%, but now it's reduced by 40%. So it's reduced by 100% minus 40%, which would be 60%, right? So 60% times x is $7. Which implies then that if we go 0.6 times x equals 7, x equals 7 divided by 0.6, which is what? 11.67. Now the problem I have with these types of questions is just because of the wording. It's been reduced by 40%. It doesn't mean it's reduced to 40%. Okay? There is a major difference. Reduced by and reduced to. Increase 310 by 95%. These are interesting. They're just tricky because they're not even really that tricky. It is a regular common thing to have in your classes or even in real life, you know. I want to increase my profits by 10%. Right? Okay. Increase Yeah, I'm not sure if there's another way to really say it. Increase 310 by 95%. So it's like you wanted to go up 95%. Now, you're not going to times by 95% because that's actually reducing it, right? So you want it to go up by 95%. So 310 times 1 plus 0.95. Which would be 604.5. What would be one? Another one she's got in here. Decrease 500 by 70%. You don't want it to go down to 70%, 70% of the original value. You want it decreased by 70%. Which means you would want to go 500 times 1 minus 0.7. Or it would go down to 30% of its original value. So 30% of that would be what, 150? And what is it, 500? Hmm. The next set in this one looks the exact same. There's no extra trick to it. It's 1 plus and 1 minus. The only thing that would be a real trick to it would be decrease by a negative percentage, right? Okay. That's enough of this one. So let's erase this one and we'll go help with our percentages real quick. Okay. If 53% of a number is 53, what is the number? Okay. A percentage is a fraction of a number. %53 is 0.53 of a fraction of a number. So let x be a number. Then 53% times x is equal to 53. 53% is 0.53 times x is equal to 53. X equals 53 over 0.53, which equals 100. Okay. Then we've got another one. 5% of a number is 57. What is the number? Okay. We are going to do again. Let x. Now, I should do it like before. I should let So then we've got 5% times x equals 57. Then we should say, well, that's 0.05 x equals 57. Divide by 0.05. So then we'd have x is equal to 57.05, which equals, what did we say? 1140. Okay. Good. Where is my mouse? There it is. Percent one. Okay. Next questions. And two. A shirt has been reduced by 40% to $7. What is the original price? So we've got a shirt has been reduced by, what did we say, 40%? 40% to $7. To $7. What was the original price? Okay, well, we say that the original price is 100%, right? It's multiplying by 1. We reduce by 40%, which means we take away 40% from 100. Means we go 100% minus 40%. Okay. And so we would have, should I write it that way? 100% minus 40%. We have to let x be the price times x is equal to $7. 60% of x is equal to 7, which means x equals, I don't like having so many lines, 0.60 equals 7, x equals 7 over 11.6, which equals, what did we say? 11.67. $11.67 times 60%, 7.002. Increase 310 by 95%. Which equals 604.5. Should write that a little nicer, yeah? Okay. Decrease 500 by 70%. So then we would have 500, 1 minus 70 equals 500 times 0.3, right, just in parentheses. Equals, well, I said 150, right? There. Good enough to me. Percentage 2. Okay. I need a quick moment to send it to myself. Too bad you can't just post straight. Okay, what did I do? I did %1, %2, and triangles. Okay, that should be all three. one and then this one. Got to type in all the hashtags too. Ugh. Hmm. Um. Okay. Now that that's done, what should we move on to next? Should we move on? We've been going for quite a few hours. Now let's keep going. Okay. Okay. Calculate the perimeter of each figure to the nearest tenth of a unit. Problems and applications. Or evaluate. You know what? These evaluation problems might be useful. So, let's figure out what would be useful for boss mom in this regard. So there's evaluate. What would be? I'm trying to think of a way to say. thinking a way to say. Well, okay. So, like, you're given some function. Let's say x squared plus 2, x plus 1. And let's say evaluate at x equals 1. How do you tell people that all you do is you just plug in 1 where x is and then solve the equation? So 1 squared plus 2 times 1 plus 1, which would give us what, 4? And x equals 2. Give us 2 squared plus 2 times 2 plus 1, which would be what, 9? Let's say x equals y plus 1. This is where people have trouble. So all I'm doing is replacing x with y plus 1. Now, why do people have trouble with this idea that all you're doing is replacing a variable, a number, with something else? So I could say x equals 3 dots. 1, 2, 3. Or x equals this triangle. If I plug it in, all I do is plug it in, right? And that's what I get. So I get 3 dots squared plus 2 times 3 dots plus 1. Don't know what 3 dots represent, but that doesn't matter. That's just plugging them in. Same thing with the triangle. Plug in the triangle, squared plus 2 times the triangle plus 1. Done. There's nothing to change. Don't know what a triangle means. We could have some kind of funky evaluation where we say 3 dots is equal to 3, and we could say this triangle is equal to 2. We could if we want. That's just a relation. What else could we say? Now, what happens when we plug in y plus 1? Well, we've got y plus 1 squared plus 2 times y plus 1 plus 1. And then simplify. Well, I've been going for several hours. I think it's time to take a break. Maybe contemplate some other stuff and come back at it fresh. And maybe we'll have more people later tonight, too. It's first school day, right? Yeah. I think that's a good idea. So I'm going to stop the stream for now, and we'll talk later.